Hi! Some time ago I participated in a running contest. I wasn't the best, but I was happy to find that my finish time of 51 minutes was at least below the group average. However, some friends pointed out to me that I had an advantage, since compared to the others in the group, my body length is relatively high and my weight is relatively low. How can we know if my friends are right? It's hard to find a group of people with exactly the same length and body mass as me to compare to. In this video, I will show you a way to tackle this problem using so-called multiple regression. Here's the idea. Instead of looking at the average finish time of the whole group, let's try to find out what the average finish time would be if we take body length and weight into account. That is, we assume that the average finish time is a function of length and weight. Of course, I don't know a precise formula for that function. The graph here is just an idea of what it might look like. But since the variation of masses and lengths of the runners in the group is not that large, it's reasonable to assume that the function can be approximated by a linear function. So, this is our model. We assume that the average finish time t depends linearly on body length L and body mass m of a runner. The question is, what are the coefficients? Well, we do have some information about this function. We can use the data from the runners in the contest. So, we record body length, body mass and finish time for all participants. This gives a bunch of data points. And then we try to find the coefficients beta 0, beta 1 and beta 2 such that the graph is as close as possible to these data points. This is precisely the type of problem that you've seen in the lecture. The only difference is that there's more than one independent variable in the model. But I will show you that exactly the same ideas work in this case. First of all, we plug in the measurement data for each runner into the model. This gives a bunch of restrictions on the coefficients in the form of linear equations. We can rewrite this system of equations as matrix vector equation. Let's call the matrix X the vector of unknown coefficients beta and the right-hand side y. To find the coefficients, we have to solve the equation x times beta equals y. However, you'll find that this equation is inconsistent, and that's not surprising. The data points that give rise to the system do not really lie on a plane, as our model assumes. But we don't give up. We can look for the least square solution by solving the normal equation. This works in exactly the same way as what you've seen in the lecture, so I will not do the calculation in detail now. You will get the following estimates for the coefficients, and these coefficients then give the best approximation of the average running time as function of body length and weight based on the runner's data. So what can we say about my finish time? Well, given my length and weight, the model predicts an average finish time of 47 minutes for people of the same length and weight as me. However, my actual finish time is 51 minutes, so it seems my friends were right. If you compensate for length and weight, I was actually slower than average. Let's ignore that and focus on the math. The principle of fitting a function of more than one variable to a data set, like I did here, is called multiple regression. It's not limited to linear models. For example, suppose that you also want to take quadratic terms of L and M into account. Then there are 6 unknown coefficients, and the point here is that the measurement data gives rise to a linear system since the model is still linear in the coefficients. And again, we can solve the corresponding normal equation to find the least square solution, and this gives the best fit for the model to the data points. Of course, you can wonder whether this model is realistic. In any case, it's not better for me. The predicted average finish time is even lower. Thanks for watching.